consisting of all the partial derivatives in the symmetric form. As long as we can do that, immediately you create a very interesting factor. Right? It is orthogonal to the all level curves. So next, I want to compute the partial derivative again, but I want to apply it in a very different way. So this is so-called tangent plane and linear approximation. Okay, linear approximation. Okay, so I want to recall again what the partial derivatives are about. Okay, I want to recall again what the partial derivatives are about. If I have a function z equals f of x and y, so z is equal to f x y. So I have a surface as the graph of the function, right? So if I pick one point, a, b, as my base point, I can compute the partial derivatives with respect to x evaluated at this point with respect to y evaluated at this point. And we discussed about the geometric meaning of the partial derivatives. All right? So fx evaluated at this point is talking about the tangent line, which is parallel to an x-axis, right? So if you draw a curve contained in the surface parallel to x-axis, and then the partial derivative with respect to x at this given point is talking about the slope of a tangent line. So basically, a tangent line right here. All right. We can also have a curve sitting on the surface parallel to y-axis. This is a curve sitting on the surface parallel to y-axis. I can also have a tangent line to this curve. All right. And we even generalize these curves into any direction. You can pick any direction, not just x or y. You can pick any direction on R2. You can have the corresponding curve sitting on the surface where you can compute the tangent line. All right? So basically, I would have a family of tangent lines at this point in different directions. Are you with me? I have a family of tangent lines to this point, to the surface. Or you can imagine you can rotate the tangent line 360 degrees. And that family of tangent lines will form a plane. And that plane will be the tangent plane. Okay, so tangent plane, you can, is equal to all the tangent lines. You can sort of understand the tangent plane as the family of all the tangent lines. So you gather all the tangent lines together, this is going to be a two-dimensional object. That's the tangent plane. So the tangent plane, in other words, contains all the tangent lines to the point. Okay, so this is the tangent line. So our goal is to derive the equation of the tangent plane. All right? So our goal is to derive the equation of the tangent plane if you know the formula of the function. Okay? If you know the formula of the function, we want to get the equation of the tangent plane. Here is the formula. So if I have a function already given in this implicit form, you remember I'm calling this as the implicit definition of function. We also have I'm sorry, this is the explicit. Okay, we also have an implicit definition of a function. Fxy of z is equal to 0. Okay? So this format of the equation will be very friendly to work with when you want to compute the equation of the tangent plane. Okay? So I want to quickly translate this format again. So x, y in this equation are the independent variables. There are three variables governed by y equation, so z is going to be the dependent variable. So this is still going to be similar to what we wrote right here. X, y are independent. Z will be changed according to the change of x, y. So this is still a two independent variable function. Okay? And the tangent plane at the point P, A, B, and C has the following equation. Fx, x minus A plus Fy, y minus B plus Fz, z minus C is equal to 0. So this will be the formula of the day. Okay. So you can immediately see why I want to choose this form for the equation. Because as long as I have this form of the equation of the function, then the equation of the tangent plane is extremely symmetric. Okay. Again, this f sub x, f sub y, and f sub z are partial derivatives. In computation, we're doing nothing more than taking derivatives, but we'll be able to use this partial derivatives in a very clever way to get the equation of the tangent plane. Okay, so this was the tangent plane, which is tangent to the surface at this given point. You can immediately check this one does pass through A, B, and C. All right. If I plug in x equals A, y equals B, C equals Z, this is exactly equal to 0. So this equation does pass through A, B, C. All right, and it will be tangent to the surface. So I want to quickly practice a couple of examples. Okay, and then I will give you why do we care about tangent plane? Why would we care about tangent plane? So if I have a function, so y z e to xy plus 10 is equal to 0. So I am at a point 0, minus 5, and 2. Okay, so I'm at the point 0, minus 5, and 2. I want to compute the equation of the tangent plane to this function. Okay. Is David here? David. Is Kevin here? Is Kevin here? Is James here? Okay, so James, work with me, please. So I want to compute the equation of the tangent plane.
Okay. So you're gonna have to calculate the partial derivative with respect to x, which is.
Or simply, I'm just going to name this whole thing as my capital F x y. All right. So what do you have?
It's just going to be e to the xy.
So in order to save your energy, let's just write it again right here. So plus f z minus c is equal to 0. So fx is going to be
e to the xy
e to the xy
times y.
times y. But I also got this constants,
So y squared.
right?
Oh, okay.
Right, so it's going to be yz again. Right, so this is the partial derivative with respect to x. And then x minus
Minus 0.
0, okay? And then plus fy is going to be, takes a bit of product rule, all right? You need to use the product rule.
Yeah.
So what do you have?
Z e to the x.
Z e to xy. Here we're taking derivative with respect to this factor, right? And then plus.
E to the xy
Mm-hmm.
times z.
Times, I need to take the derivative with respect to this factor, all right? Forget about this one first. So taking derivative with respect to this factor, you're getting e to xy times x, all right? And then times everything which is left. Okay? So this is the product rule. And multiply by y minus 5 is plus 5. Okay? And partial derivative with respect to z, and that's the easy one. Plus y
E to the xy.
e to xy. Okay. And then z minus 0 is equal to, I'm sorry, z minus 2 is equal to 0. And then I need to plug in these values. X equals 0, y equals minus 5, and z equals 2. Okay? Because x is equal to 0, these exponentials are all going to be equal to 1. All right? So these are pretty easy to evaluate. X equals 0, exponential is equal to 1, y is equal to minus 5, y is x equals 2. What do we have?
50x.
So it's going to be 50x plus. So it's going to be 2 plus 0. So it's 2 y plus 5. What's the very end?
Just -5.
Minus 5 z minus 2 is equal to 0. Okay? So we can break all the parentheses and pull the numbers out. So it will be 50x plus 2y minus 5z. I have a plus 10 and then a plus 10, so it's plus 20 is equal to 0. Am I right? Yep. Am I making any mistake? Let's see, I'm taking derivative with respect to x. And so what do we have? So minus 5 times z equals 2, so we're getting a 50 right here. Am I making any mistake? Michael?
No, it's just the 10. Just forgot about it.
Which 10?
The constant at the top, it all goes.
Oh,
away.
yeah, that's right.
It all goes away.
No, that's
No,
plus 10.
that's irrelevant.
Yeah,
No, that's irrelevant.
never mind.
I don't have that, that's plus 10 anyway.
It was irrelevant.
You almost scared me. No. I don't think I have made any mistake. And there's no further common factor I can remove out of the 4 numbers. So this is pretty much it is. Okay? So this is the equation of the tangent plane and its given point. Yeah, Michael.
Can we leave it in that? Though, can we leave it without being simplified, so we can just leave it as step before?
I'm okay with that, but I'm not sure whether the online homework system is okay with that. So you better check with them. They're not. No. The numbers are not that scary, so it's just a matter of simplification. Okay? Okay, so instead of giving more examples, I want to observe some interesting things, which will give you the reason why we're interested in finding the equation of the tangent plane. So this is going to be the general formula. This general formula should be also okay if I have the formula in this explicit form. All right, so I want to derive the equation of the tangent plane when my equation is z equals fxy. Okay, so if I know z is equal to fxy, I still want to use this formula. I need to design a capital F. All right, so the capital F I'm going to design is going to be naturally, say, z or fxy minus z. Probably it's going to be here. So fxy minus z. Okay. So this is the equation I designed, fxyz. All right. So I have a capital equation with 3 variables. Then this equation z equals fxy will be equivalent to capital F equals 0. That was me. Therefore, I will be able to use this formula right here. So basically, I want to see the equation of the tangent plane when my equation is z equals a small f. But the only available formula here involves a symmetric form, so I have to design a way to use this symmetric formula. Okay? That was me. So fxy z is equal to 0. It's going to be my new function. Okay? This is going to be my new function. The function is just the small f minus z right here. So the tangent line, the tangent plane has the equation x minus a plus fy, y minus b plus fz, z minus c is equal to 0. Okay? So the only thing I need to do is to take the partial derivatives with respect to this function. All right? I just need to take partial derivatives for this function right here. Yeah? So if I'm computing the partial derivative with respect to x, what do you have here? It's just small f of x. Am I right? Just small f of x. Yes? Okay, so x minus a. If I take the partial derivative with respect to y, I'm just getting small f of y, y minus b. If I take the partial derivative with respect to z, it's going to be minus 1. C minus C. But indeed, if I have x equals A, y equals B, my C has to be small f of AB is equal to 0. Okay? Now the only thing I'm saying here is, if x is equal to A, y is equal to B, at ABC with respect to capital F, when you go back to small f, it's just z equals f of AB. So we are at the point A, B, and f of AB if you want to plug in the symmetric form with respect to capital F. Right? That's the only thing I'm doing here. Okay?
Why
Yep.
is it 1 instead of f of z?
Okay, so this is the function. I want to take derivative with respect to z.
Oh, with respect to
Which
Z.
just goes,
Right? So capital F sub z, when you take the derivative with respect to z, you're just getting a minus 1 right here. Right?
Oh.
This is exactly what you did when you do the implicit differentiation deal. Okay? And then amazing thing happens. I will be able to simplify this whole thing to get the equation of the tangent plane for z is equal to small fxy. So this is going to be fx x minus a plus fy of y minus b. And I can even move these terms around. So z is equal to this whole thing plus f of ab. Okay, so this would be the equation of the tangent plane if you have a function defined by z is equal to fx. This one is still pretty symmetric if you look at it more carefully. Okay, if you look at it more carefully. So z is equal to partial derivative times x minus a. This whole thing is essentially talking about dot of x. Am I right? And fx, as we already agreed on, is talking about rate of change, right? And this part is talking about dot of y, and f sub y as the partial derivative is talking about rate of change. So essentially, I'm talking about z is equal to change happen because of x is changed, change happens because y is changed plus the original value we have. That with me?
Yeah.
So I want to find the function value after the change. This is the function value before the change. Right? So from AB to x and y. So x is changed by dot x right here, y is changed by dot y right here. Because I have two independent variables, I need